Hello there, and welcome to something completely different. Tonight, we're going to explore one of nature's most powerful forces in a way you've probably never experienced before. We're diving into the gentle, soothing world of earthquake science, where the very ground beneath your feet holds secrets that are surprisingly calming to discover. I know what you're thinking. Earthquakes? Relaxing? But trust me on this journey. There's something profoundly peaceful about understanding the slow, patient rhythms of our planet. The way tectonic plates drift like continents of stone floating on an ocean of molten rock. The quiet accumulation of stress over decades, even centuries, before releasing in moments that reshape the world. Tonight, we'll wander through the science of seismic waves, explore the hidden beauty of fault lines, and discover why our restless planet is actually following patterns more predictable and gentle than you might imagine. Each fact will be like a soft wave washing over you, carrying you deeper into understanding and further toward rest. If you find yourself drifting off during this exploration, that's exactly what should happen. You can like this video if it helps you sleep, subscribe if you'd like more peaceful science in your life, or simply let these geological wonders carry you into dreams. But for now, just get comfortable. Let your breathing slow and allow the ancient wisdom of earthquakes to settle gently around you. Let's begin with something that might surprise you. The earth beneath you right now is moving. Not quickly, not violently, but with the patient persistence of geological time. Your house, your bed, the ground outside your window, all of it is drifting slowly across the planet's surface at about the same speed your fingernails grow. 2 to 4 inches per year, carried along on massive plates of rock that float like rafts on the Earth's molten interior. This movement is so gradual, so consistent, that it's been happening for billions of years without pause. Right now, as you listen to these words, North America is creeping westward, while the Atlantic Ocean grows wider by the width of a coin each year. It's a process so slow and steady that entire mountain ranges rise and fall in this gentle dance of stone. The San Andreas Fault in California isn't a crack in the ground waiting to swallow cities. It's more like the seam between two massive pieces of the Earth's crust, sliding past each other with the patience of geological time. Most of the time, this movement happens so smoothly that sensitive instruments can barely detect it. The plates glide past each other millimeter by millimeter, releasing their energy in tiny increments too small for humans to feel. Scientists call this creeping motion a seismic slip, and it's happening right now along thousands of fault lines around the world. It's the Earth's way of relieving stress gradually, like stretching after a long day. This quiet movement prevents the buildup of tension that might otherwise release all at once. There's something deeply calming about imagining this process. The Earth, in its wisdom, has found ways to move and change without drama, without violence. Most tectonic motion happens in silence, in darkness, far below our daily lives. It's been going on since long before humans existed, and it will continue long after we're gone, following rhythms older than life itself. Even when earthquakes do occur, they follow patterns that reveal the Earth's underlying order. Seismic waves travel through rock at predictable speeds, following the same physical laws that govern sound waves in air or ripples in water. P waves, the primary waves, race ahead at about 4 miles per second, compressing and expanding the rock they pass through like a gentle massage deep in the earth. Following behind come the S waves, secondary waves that move more slowly, swaying the ground from side to side with a rolling motion that's almost musical in its rhythm. These waves carry information about the earthquake's source, its depth, its magnitude, all encoded in the way they make the ground dance. Scientists can read these wave patterns like sheet music, understanding the Earth's composition by listening to how seismic energy travels through different layers of rock. The way waves slow down in soft sediment, speed up through solid granite, or reflect off the boundaries between different types of stone tells a story about what lies beneath our feet. Deep in the Earth's core, 2,900 kilometers below the surface, seismic waves reveal an ocean of liquid iron, slowly churning and generating the magnetic field that protects our planet from harmful solar radiation. Even deeper, at the very center, lies a solid iron sphere nearly as hot as the surface of the sun, yet held in crystalline form by the immense pressure of all the rock above it. This inner core spins slightly faster than the rest of the planet, completing an extra rotation about every 400 years. It's like a heart beating inside the Earth, maintaining the rhythms that keep our magnetic shield strong and stable. The entire system works together in harmony, layers upon layers of rock and metal, each following its own patient patterns. Earthquakes themselves follow a beautiful mathematical relationship called the Gutenberg-Richter law. For every large earthquake, there are 10 times as many earthquakes 1 magnitude smaller, and 100 times as many 2 magnitudes smaller. It's a scaling pattern found throughout nature, from the branching of rivers to the distribution of galaxies in space. This means that while dramatic, destructive earthquakes capture our attention, they're vastly outnumbered by tiny tremors that happen constantly around the world. Every day, thousands of micro-earthquakes occur, so small that only the most sensitive instruments can detect them. They're like the Earth's quiet breathing, a constant gentle reminder that our planet is alive and dynamic. Many of these small earthquakes happen in places where no one lives to feel them. Deep ocean ridges where new seafloor is being born, remote mountain ranges where ancient rocks are slowly adjusting to changing pressures, or far beneath the surface where the motion is absorbed by layers of soft sediment before it can reach the ground above. The ocean floor is actually the most seismically active place on Earth, with underwater earthquakes happening almost continuously along the mid-ocean ridges. These submarine tremors rarely affect anyone, occurring instead in the peaceful darkness of the deep sea, where their energy dissipates harmlessly into the vast volume of water above. Even the timing of earthquakes reveals patterns that speak to the Earth's orderly nature. Some faults have characteristic earthquake intervals, producing similar-sized tremors every few decades or centuries with remarkable consistency. The Parkfield section of the San Andreas Fault in California was so regular in its magnitude 6 earthquakes, occurring roughly every 22 years, that scientists attempted to predict the next one. While that particular prediction didn't work out exactly as expected, it revealed something beautiful about how the Earth manages stress and release. Like a clockwork mechanism made of stone, some parts of our planet follow rhythms we can almost set our calendars by. Earthquake prediction may be impossible in the short term, but earthquake preparation follows well-understood principles. Buildings can be designed to sway gracefully with seismic waves rather than fighting against them. Modern skyscrapers in earthquake-prone areas are marvels of engineering, able to bend and flex like trees in the wind, returning to their original position once the shaking stops. The science of seismology has given us tools to understand and live peacefully with the Earth's restless nature. Seismometers can detect ground motion smaller than the width of an atom, sensitive enough to record waves from earthquakes on the opposite side of the planet. These instruments reveal that the Earth is never truly still, always humming with tiny vibrations from wind, ocean waves, and the distant rumble of human activity. This background noise of the Earth, called microseisms, creates a constant low-frequency melody that seismologists learn to filter out when studying earthquakes. It's like the planet's heartbeat, a gentle rhythm that never stops, connecting every point on the surface through vibrations traveling through solid rock. The study of earthquakes has also revealed the beautiful complexity of how stress propagates through the Earth's crust. When one fault moves, it can trigger cascades of smaller movements on nearby faults, like dominoes falling in slow motion over periods of years or decades. This process, called stress transfer, shows how interconnected our planet's geology really is. Every earthquake slightly changes the stress on surrounding faults, sometimes bringing them closer to their next rupture, sometimes postponing it for years. It's a delicate balance, a conversation between different parts of the Earth's crust, conducted through the language of pressure and release. Scientists have discovered that some earthquakes can even trigger others on the opposite side of the planet. Large earthquakes generate seismic waves that travel all the way through the Earth's core, emerging on the far side with enough energy to nudge already stressed faults into motion. The planet responds as a unified system with events in one location influencing conditions thousands of miles away. This global connectivity extends to the very deepest earthquakes, which occur not at the surface but hundreds of kilometers down in subducting slabs of oceanic crust. These deep earthquakes happen in conditions so extreme, with pressure so intense, that the rock behaves in ways we're still learning to understand. At such depths, the normal processes that cause shallow earthquakes may not apply. Instead, the rock might undergo phase transitions, sudden changes in crystal structure that release energy in earthquake-like bursts. It's geology at the molecular level, where the arrangement of atoms determines how the planet moves and shakes. The deepest earthquake ever recorded occurred nearly 700 kilometers below the surface, in rock so hot and compressed that it challenges our understanding of what makes earthquakes possible. These deep tremors remind us that the Earth's interior follows rules we're still discovering, processes that happen in conditions no laboratory can recreate. Yet even in these extreme depths, there's a remarkable consistency to how the Earth behaves. The same physical principles that govern shallow earthquakes apply in modified form hundreds of kilometers down. Stress accumulates, rock reaches its breaking point, energy releases, and the cycle begins again. It's a pattern repeated at every level of the Earth's structure, from the thinnest surface layers to the deepest subduction zones. The way earthquake energy travels through our planet reveals its internal architecture with stunning clarity. When seismic waves encounter the boundary between the Earth's mantle and its liquid outer core, they behave exactly as physics predicts. Some reflecting back toward the surface, others refracting and continuing their journey through the molten iron below. This creates shadow zones on the Earth's surface where certain types of waves simply cannot reach. Geometric patterns of silence that map the planet's hidden geometry. These seismic shadows were among the first clues that led scientists to understand the Earth's layered structure. The way earthquake waves bend and reflect as they travel through different materials is like having an X-ray vision into the planet's interior. Each earthquake becomes a flashlight illuminating the darkness below, revealing the boundaries between solid and liquid, dense and light, hot and cool. The temperature deep in the earth follows gradients so smooth they seem almost designed for stability. Heat flows outward from the core through the mantle at rates measured over millions of years, driving the convection currents that move tectonic plates at the surface. It's an engine powered by the planet's original formation heat and the steady decay of radioactive elements, running continuously for over 4 billion years without pause. This heat engine operates with remarkable efficiency, transferring energy from the core to the surface through processes that maintain the Earth's magnetic field, drive plate tectonics, and shape the landscape we see today. Every mountain range, every ocean basin, every fault line is ultimately powered by this steady flow of thermal energy from deep within the planet. The magnetic field generated by this process creates an invisible shield that extends far into space, deflecting harmful solar radiation and protecting the atmosphere that makes life possible. Without earthquakes and the tectonic processes they represent, this protective field would gradually weaken, leaving Earth vulnerable to the solar wind that stripped away Mars's atmosphere billions of years ago. In this way, earthquakes are not just geological phenomena, but essential components of the planetary system that maintains our world's habitability. The same forces that occasionally shake the ground are continuously working to preserve the conditions necessary for life. It's a reminder that what might seem destructive at human timescales serves vital functions across the vastness of geological time. The study of ancient earthquakes, preserved in rock layers and sediment cores, reveals that the Earth's seismic patterns have remained remarkably stable over millions of years. Fault systems that are active today show evidence of similar activity stretching back through deep time, following the same basic patterns generation after generation. There's something deeply reassuring about this consistency, this evidence that the Earth's restless energy follows predictable channels. Paleoseismology, the science of prehistoric earthquakes, reads the Earth's memory stored in displaced rock layers, offset stream beds, and disturbed sediment sequences. Each ancient earthquake leaves its signature in the geological record, creating a library of seismic history that extends far beyond human memory. Scientists can trace individual fault systems back thousands of years, watching their behavior patterns emerge from the patient accumulation of evidence. These geological records show that even the largest earthquakes, the rare great ruptures that reshape entire regions, occur within cycles that span centuries or millennia. The Earth remembers its stress patterns, repeating similar sequences of buildup and release across time periods, so vast they dwarf human civilization. Yet the underlying rhythms remain comprehensible, following mathematical relationships that reveal order within apparent chaos. The way earthquakes cluster in time and space creates patterns visible only when viewed across decades or centuries. Periods of increased activity alternate with quieter intervals, like breathing cycles scaled to geological time. Some regions experience swarms of moderate earthquakes that release stress gradually, while others store energy for longer periods before releasing it in single, larger events. These temporal patterns suggest that the Earth has preferred ways of managing tectonic stress, strategies that have evolved over billions of years of planetary evolution. The fault systems we see today are the survivors, the configurations that have proven most stable and efficient at accommodating the planet's internal forces. They represent solutions tested and refined across unimaginable stretches of time. Even the geometry of fault networks reveals underlying principles of efficiency and stability. Faults tend to connect and intersect in ways that minimize the overall energy required to accommodate tectonic motion. Like river systems finding the most efficient path to the sea, fault systems evolve toward configurations that allow the Earth's crust to deform with the least resistance. The angles at which faults intersect, the spacing between parallel fault strands, the depth at which they merge or separate, all follow mathematical relationships that optimize stress distribution. It's as if the Earth has solved complex engineering problems through millions of years of trial and error, arriving at fault geometries that balance strength and flexibility. These optimized fault systems create a kind of seismic infrastructure, channeling tectonic forces along pathways that have been tested and refined over geological time. When earthquakes occur, they're following routes established by countless previous events, traveling along fault surfaces polished smooth by millions of years of gradual motion. The smoothness of mature fault surfaces is remarkable, ground to mirror-like finish by the constant grinding of rock against rock. This polishing process, called fault gouge formation, creates clay-like materials that can actually lubricate fault motion, making it easier for plates to slide past each other. The Earth manufactures its own lubricants, reducing friction and promoting the smooth motion that prevents stress buildup. In some cases, these fault zone materials become so smooth and weak that they allow tectonic plates to slide past each other almost continuously, creating aseismic creep that releases stress without generating earthquakes at all. The Calaveras Fault in California moves this way in many places, accommodating several millimeters of motion per year, so gradually that buildings constructed across it simply bend and flex without damage. This fault creep can be so steady that scientists use it as a natural laboratory for studying how rocks behave under stress. Measurements taken over decades reveal motion so consistent it resembles the smooth operation of a well-oiled machine, with stress and strain balanced in perfect equilibrium, its tectonic motion reduced to its most essential and peaceful form. The instruments that measure this subtle motion are marvels of precision, capable of detecting changes smaller than the thermal expansion caused by temperature variations throughout the day. GPS receivers can track the gradual drift of points on the Earth's surface with millimeter accuracy, revealing the slow dance of continents that unfolds around us constantly. These measurements show that tectonic motion is not random or chaotic, but follows vector fields that can be mapped and predicted. Each point on the Earth's surface has a specific velocity, moving in a particular direction at a measurable rate. The resulting maps look like weather charts, showing the flow of solid rock as if it were a slow-motion fluid. The beauty of these velocity fields lies in their smoothness and coherence. Adjacent areas move in similar directions at similar speeds, creating gradual gradients of motion that extend across entire continents. Only at plate boundaries do these smooth patterns change abruptly, marking the locations where different pieces of the Earth's puzzle meet and interact. Between these boundaries, in the stable interiors of tectonic plates, the motion is so uniform that points thousands of kilometers apart move together as if they were parts of a single rigid body. It's this rigidity that allows continents to hold together despite the constant motion, preserving the familiar shapes of land masses across millions of years of drift. The forces that drive this motion operate on scales that dwarf human experience, yet they follow the same physical principles that govern motion in the everyday world. Newton's laws of motion apply as much to drifting continents as to rolling balls, just scaled up by factors of billions in mass and time. The Earth's plates accelerate, decelerate, and change direction in response to forces, just like any other moving object. These forces arise from temperature differences in the Earth's interior, which create convection currents in the mantle that drag the overlying plates along like leaves on a stream. The hottest material rises from near the core, cools as it approaches the surface, then sinks back down to be reheated and rise again. It's a heat engine powered by the temperature difference between the Earth's hot interior and cold surface. This convective flow has been running continuously since the Earth's formation, stirring the planet's interior and driving the surface motion we observe as plate tectonics. The patterns of rising and sinking material create a three-dimensional circulation that connects every part of the mantle, from just below the crust to the boundaries of the liquid core 2,900 kilometers down. The timescales of this circulation are vast, with material taking tens of millions of years to complete a single cycle from surface to core and back again. Yet this slow stirring is what maintains the Earth's magnetic field, drives volcanic activity, and shapes the surface features we see today. Every mountain, every ocean basin, every earthquake fault is ultimately connected to this deep circulation system. Understanding these connections reveals earthquakes not as isolated disasters, but as surface expressions of the planet's fundamental life processes. They are symptoms of a living world, evidence that the Earth remains active and dynamic after more than 4 billion years of evolution. In this context, seismic activity becomes not something to fear, but something to appreciate as part of the grand machinery that keeps our planet habitable. The relationship between earthquakes and the ocean reveals another layer of the Earth's gentle complexity. Beneath the waves, where sunlight never reaches, the seafloor spreads apart at mid-ocean ridges with the patience of geological time. Here, new oceanic crust is born continuously, emerging from the mantle as molten rock that cools and solidifies in the darkness of the deep sea. This process happens so gradually that it's almost meditative to contemplate. Along the mid-Atlantic ridge, which runs like a spine down the center of the Atlantic Ocean, new seafloor emerges at about the rate your hair grows. The ridge itself is a gentle swell on the ocean floor, rising only a few kilometers above the surrounding abyssal plains, yet it represents one of the most fundamental creative forces on our planet. The earthquakes that occur along these underwater mountain ranges are typically small and frequent. Like the Earth's quiet breathing, they mark the spots where fresh rock breaks free from the mantle and begins its journey across the ocean floor. Each tremor is a birth announcement, signaling the creation of new planetary surface that will eventually travel thousands of kilometers before returning to the mantle at a distant subduction zone. The symmetry of this process is beautiful in its simplicity. As new seafloor spreads away from the ridges, it carries with it a magnetic signature frozen into the cooling rock. These magnetic stripes, alternating in polarity as the Earth's magnetic field has reversed through time, create patterns on the ocean floor that mirror center. Reading these magnetic patterns is each other perfectly on either side of the spreading, like examining tree rings, except these rings record the Earth's magnetic history over millions of years. Scientists can trace individual magnetic reversals across entire ocean basins, watching how they spread outward from the ridges like ripples from a stone dropped in still water. The regularity of these patterns reveals that seafloor spreading has proceeded at remarkably constant rates for tens of millions of years. This constancy extends to the earthquakes themselves. The seismic activity along mid-ocean ridges follows predictable patterns, with smaller earthquakes occurring almost continuously and larger ones maintaining statistical relationships that have remained stable across geological time. It's as if the Earth has found its optimal rhythm for creating new oceanic crust, a pace that balances efficiency with stability. The transform faults that offset these spreading centers add another layer of geometric beauty to the system. These fractures run perpendicular to the ridges, accommodating the slight variations in spreading direction that occur as the curved Earth's surface tries to open along straight lines. The result is a pattern that resembles a zipper, with the ridge segments connected by transform fault links that allow the entire system to flex and adjust. The earthquakes on these transform faults are different from those at the spreading centers, occurring along surfaces that slide past each other horizontally rather than pulling apart. Yet they too follow predictable patterns, with stress building gradually until it releases in sudden slips that realign the ridge segments. The timing of these events can be remarkably regular, with some transform faults producing similar earthquakes every few years, with clockwork precision. Far from these active spreading centers, the ocean floor settles into a peaceful existence. As oceanic crust moves away from its birthplace at the ridge, it cools and contracts, gradually sinking deeper into the ocean as it ages. This thermal subsidence follows mathematical curves that scientists can predict with remarkable accuracy, showing how the Earth's surface responds to cooling over millions of years. The older portions of oceanic crust are among the most seismically quiet places on Earth. Here, far from active plate boundaries, earthquakes are rare events that often go unnoticed except by the most sensitive instruments. The thick blanket of sediment that accumulates over millions of years helps dampen any small tremors that might occur, creating regions of profound geological calm. These sedimentary blankets tell their own stories of time and patience. Layer upon layer of microscopic marine organisms, dust from distant continents, and volcanic ash from eruptions around the world accumulate grain by grain, creating archives of Earth's history that stretch back hundreds of millions of years. The weight of these accumulating sediments gradually compresses the underlying oceanic crust, contributing to its slow subsidence into the deep ocean basins. When oceanic crust finally reaches a subduction zone after its long journey across the seafloor, it begins a new phase of its geological life cycle. Here, the dense oceanic plate slides beneath the lighter continental crust, descending back into the Earth's interior, where it will eventually be recycled into new mantle material. This process, too, generates earthquakes, but ones that follow their own distinct patterns. Subduction zone earthquakes occur in a three-dimensional space that extends hundreds of kilometers into the Earth's interior. The descending slab of oceanic crust remains cooler than the surrounding mantle rock for millions of years, creating a zone of different material properties that extends deep into the planet. Earthquakes within this zone trace out the shape of the subducting slab, revealing its geometry with remarkable precision. The deepest of these earthquakes occur at depths where the pressure is so intense that the very nature of earthquake processes may be different from what happens near the surface. At depths greater than 300 kilometers, the rock is so hot and under such pressure that normal brittle fracturing becomes difficult. Instead, earthquakes may result from sudden changes in the crystal structure of minerals, phase transitions that release energy in seismic waves. These deep earthquakes create some of the most beautiful seismic wave patterns recorded by instruments around the world. Because they occur so far below the surface, their energy travels through nearly the entire Earth before reaching seismometers on the opposite side of the planet. The resulting seismograms show waves that have sampled the planet's internal structure from core to surface, carrying information about conditions thousands of kilometers below ground. The journey of these seismic waves through the Earth follows paths that curve and bend according to the varying properties of rock at different depths. Waves travel faster through cooler, denser material and slower through hotter, less dense regions. This creates ray paths that curve like light bending through a lens, focusing and defocusing the seismic energy in patterns that reveal the Earth's internal temperature structure. Scientists can use these wave paths to create images of the Earth's interior, much like medical CT scans create images of the human body. The resulting pictures show plumes of hot material rising from the deep mantle, cold slabs of subducted oceanic crust descending toward the core, and circulation patterns that connect surface plate motions to processes happening thousands of kilometers below. These images reveal that the Earth's interior is far from static. Convection currents that drive plate tectonics create a dynamic system where material constantly circulates between surface and depth. Hot material rises in broad plumes that may feed volcanic hotspots like Hawaii, while cold material sinks in narrow sheets that correspond to subducted oceanic plates. The entire system resembles a slow-motion thunderstorm with updrafts and downdrafts operating across millions of years instead of hours. The timescales of this deep circulation help explain why earthquake patterns remain so consistent over human timescales. While individual earthquakes are unpredictable in their precise timing, the overall system that generates them operates according to processes that unfold over millions of years. From our perspective, these driving forces appear essentially constant, creating the statistical regularities that allow scientists to assess seismic hazards and design earthquake-resistant structures. The study of earthquake cycles reveals patterns that operate across multiple timescales simultaneously. Individual fault segments may rupture every few decades or centuries, but the larger fault systems they belong to follow longer cycles that span thousands of years. These nested cycles create hierarchies of seismic activity, with smaller earthquakes occurring frequently within longer periods punctuated by rare great earthquakes. Understanding these nested cycles requires looking at earthquake records that extend far beyond human historical accounts. Tree rings, lake sediments, and uplifted shorelines preserve evidence of past earthquakes that can extend these records back thousands of years. Each type of evidence captures different aspects of seismic history, creating a multi-layered view of how fault systems behave over time. Tree rings can record the sudden growth changes that occur when earthquakes alter local hydrology or damage root systems. Lake sediments preserve the turbidites, underwater landslides triggered by strong shaking that create distinctive layers in the sedimentary record. Uplifted marine terraces show where ancient earthquakes permanently raised sections of coastline above sea level, creating step-like landscapes that record the cumulative effects of many seismic events. Combining these different types of evidence creates earthquake chronologies that reveal the long-term behavior of fault systems. Some faults show remarkably regular behavior, producing similar earthquakes at predictable intervals over thousands of years. Others display more complex patterns, with clusters of activity separated by longer quiet periods, or gradual changes in earthquake size and frequency that unfolded over millennia. These long-term patterns suggest that fault systems evolve and mature over geological time, gradually adjusting their behavior in response to changing stress conditions and evolving fault zone properties. Young fault systems may produce more irregular earthquake sequences as they establish their preferred rupture patterns, while mature systems settle into more predictable cycles that can persist for hundreds of thousands of years. The evolution of fault systems also involves changes in their physical properties that occur over much longer timescales than individual earthquake cycles. The repeated rupturing and healing of fault surfaces gradually changes their strength, roughness, and permeability. Clay minerals form from the grinding of rock during earthquakes, creating fault gouge that may lubricate future motion or, in some cases, strengthen the fault zone. Chemical processes also play a role in fault evolution, with groundwater circulation along fracture networks leading to mineral precipitation that can seal cracks or, alternatively, to dissolution that weakens the rock. These chemical changes occur over thousands to millions of years, gradually modifying fault zone properties in ways that influence earthquake behavior on human timescales. The interaction between these physical and chemical processes creates feedback loops that help stabilize fault system behavior over long periods. Faults that produce frequent earthquakes may develop properties that promote continued seismic activity, while those that remain locked for long periods may evolve characteristics that make future ruptures more likely. These feedback mechanisms help explain why earthquake patterns, while never perfectly predictable, show statistical regularities that persist across geological time. Understanding these long-term evolutionary processes provides context for the earthquakes we experience today. Each tremor is part of an ongoing conversation between tectonic forces and fault zone properties that has been developing for millions of years. The patterns we observe in modern seismic activity reflect this deep history, carrying forward the accumulated effects of countless previous earthquake cycles. This perspective transforms earthquakes from isolated catastrophic events into expressions of the Earth's ongoing evolution. They become part of the planet's natural rhythm, no more random or chaotic than the cycles of erosion and deposition that shape landscapes or the convection patterns that drive weather systems. Like these other natural processes, earthquakes follow physical laws that create order within apparent randomness, patterns that emerge from the interaction of simple rules operating across vast scales of space and time. The mathematical relationships that describe earthquake statistics reveal this underlying order with remarkable clarity. The way earthquake frequencies scale with magnitude, the spatial clustering of seismic activity, the temporal patterns of aftershock sequences, all follow power laws and other mathematical distributions that appear throughout the natural world. These relationships suggest that earthquake systems are examples of complex adaptive systems, networks of interacting elements that self-organize into patterns displaying both stability and change. This mathematical beauty extends to the seismic waves themselves, which propagate through the Earth according to elegant wave equations that describe how energy moves through elastic media. The way these waves reflect, refract, and interfere as they encounter boundaries between different rock types creates patterns that are both complex and predictable, following principles that allow scientists to image the Earth's interior with remarkable precision. The instruments that detect these waves have evolved into marvels of sensitivity and precision, capable of measuring ground motions smaller than atomic dimensions. Modern seismometers can detect the subtle tidal deformation of solid rock caused by the gravitational pull of the sun and moon, revealing that even apparently solid ground participates in the celestial dance of astronomical forces. These tidal effects on earthquake occurrence provide another example of the Earth's responsiveness to external influences. Some studies suggest that earthquake rates may vary slightly with tidal cycles, as the small additional stresses imposed by tidal deformation occasionally provide the final trigger for faults that are already close to failure. While these effects are subtle, they demonstrate the interconnected nature of Earth systems, where influences from space, sea, and solid ground all contribute to the complex patterns of seismic activity. The global nature of these connections becomes apparent when examining how large earthquakes can influence seismic activity on the opposite side of the planet. The passage of seismic waves from great earthquakes can trigger small earthquakes in distant regions, particularly in areas where active geothermal or volcanic systems have already brought rocks close to their failure threshold. These remote triggering events show that the Earth responds as a unified system, with disturbances in one region propagating influences across the entire planet. This global connectivity operates across multiple timescales, from the immediate triggering effects that occur minutes after large earthquakes to longer-term stress changes that may influence regional seismic activity for years or decades. The 2004 Sumatra earthquake, for example, was so large that it affected stress conditions on faults around the world, potentially advancing or delaying future earthquakes in regions thousands of kilometers from the original rupture. These far-field effects remind us that earthquake hazard assessment must consider not only local fault systems, but also the global context of seismic activity. A comprehensive understanding of earthquake risk requires appreciating the Earth as an integrated system, where local events participate in planetary-scale processes that connect every region to every other region through the medium of solid rock and the seismic waves that travel through it. The mathematics of earthquake cycles reveals patterns that operate like clockwork mechanisms made of stone. Scientists have discovered that some fault systems produce earthquakes with such regularity that they can predict general time frames decades in advance. The Parkfield section of the San Andreas Fault became famous for its approximately 22-year cycle of magnitude 6 earthquakes, each event occurring with the punctuality of a geological metronome. This predictability emerges from the steady loading of tectonic stress at rates that remain constant over human lifespans. Like a spring being compressed at a steady rate, the fault accumulates energy until it reaches its breaking point, then releases that energy in a sudden rupture before beginning the cycle anew. The beauty lies in how consistent these loading rates can be, maintained by deep mantle processes that operate with remarkable stability across millions of years. Even when individual earthquakes don't follow these cycles perfectly, they reveal other patterns that speak to the Earth's underlying order. Aftershock sequences follow a mathematical law discovered in 1894 by Japanese seismologist Fusakichi Omori, describing how the rate of smaller earthquakes following a main shock decreases predictably over time. This relationship holds true for earthquake sequences around the world, from tiny tremors to the largest ruptures ever recorded. The Omori law reveals something profound about how rocks respond to sudden stress changes. When a fault ruptures, it doesn't just release energy and return to normal. Instead, it enters a period of adjustment where the surrounding rock gradually adapts to its new configuration. Thousands of small earthquakes redistribute stress across the fault network like a musical instrument settling into tune after being struck. This adjustment process can last for years or even decades after major earthquakes, creating opportunities to study how fault systems heal and evolve. Scientists monitoring aftershock sequences observe the gradual strengthening of fault surfaces as they reestablish contact and the slow migration of seismic activity as stress redistributes through the surrounding rock network. It's a healing process that follows mathematical patterns, revealing the Earth's systematic approach to managing tectonic trauma. The spatial patterns of aftershocks also follow predictable rules, clustering near the original fault rupture in ways that illuminate the three-dimensional structure of fault systems. These patterns show how earthquakes don't occur on simple planar surfaces, but within complex networks of interconnected fractures that extend for kilometers in all directions from the main fault trace. Modern earthquake monitoring networks can map these fracture networks in exquisite detail, creating three-dimensional images of fault systems that resemble underground river deltas or root systems of enormous trees. Each small earthquake adds another point to these maps, gradually revealing the hidden architecture of stress and strain that shapes the Earth's crust. The technology that makes this mapping possible operates continuously around the world, creating a global nervous system that feels every tremor larger than magnitude 5 within minutes of its occurrence. This network consists of thousands of seismometers connected through communication systems that relay data to processing centers where computers automatically analyze each signal for signs of seismic activity. The speed and sensitivity of modern earthquake detection systems would seem magical to scientists from just a few decades ago. Earthquakes occurring on the other side of the planet are now detected and located within minutes, with magnitude estimates accurate to within a few tenths of a unit. This rapid response capability enables tsunami warning systems that can alert coastal populations to approaching waves generated by undersea earthquakes. The same technology that enables rapid earthquake detection also reveals the constant background hum of seismic activity that surrounds us always. Sensitive instruments record not only earthquakes, but also the vibrations caused by ocean waves, wind, human activity, and even the slight deformation of solid rock caused by atmospheric pressure changes. This background noise, initially seen as interference, has become a valuable source of information about Earth processes. Microseisms generated by ocean waves create continuous signals that vary with weather patterns and seasonal changes in storm activity. Scientists can track major storms across ocean basins by monitoring the seismic waves they generate, creating a weather observation system that operates through solid rock rather than through the atmosphere. These oceanic signals travel through the Earth's crust at speeds much faster than the storms themselves, providing early indicators of approaching weather systems. The study of these background vibrations has also revealed that the Earth rings like a bell after large earthquakes, vibrating at specific frequencies determined by its size, shape, and internal structure. These free oscillations, too slow to be felt but detectable by sensitive instruments, continue for days after great earthquakes, gradually decaying as the planet's internal friction dissipates their energy. Recording these planetary vibrations provides another way to study the Earth's interior structure, complementing the information gained from analyzing seismic wave propagation. Different vibrational modes sample different parts of the Earth's interior, creating a kind of seismic spectroscopy that reveals details about temperature, composition, and physical state at depths impossible to reach directly. The frequencies of these vibrations are incredibly low, with periods measured in minutes rather than seconds. The deepest modes have periods of nearly an hour, corresponding to standing waves that span the entire diameter of the Earth. Detecting and measuring these ultra-low frequency signals requires instruments capable of maintaining stability over many hours, filtering out all the shorter period noise while preserving the subtle planetary harmonics. These measurements have revealed that the Earth's free oscillations change slightly over time, reflecting long-term variations in the planet's internal structure and rotation. Earthquakes can permanently alter some of these frequencies by redistributing mass within the Earth, while seasonal changes in atmospheric and oceanic loading create predictable variations in others. The planet's vibrational spectrum becomes a diagnostic tool for monitoring global-scale changes in Earth systems. The same principles that govern earthquake-generated vibrations also explain how seismic waves can be used to explore the structure beneath individual regions. Local earthquake tomography uses waves from small earthquakes to create detailed images of fault systems, magma chambers, and sedimentary basins. The technique works like medical CT scanning, combining information from many different wave paths to reconstruct three-dimensional images of underground structures. These tomographic images reveal fault systems in unprecedented detail, showing how they connect at depth and how they interact with other geological features. Earthquake hypocenters cluster along planar surfaces that extend for kilometers underground, illuminating fault geometries that would be impossible to map from surface observations alone. The resulting images look like X-rays of the Earth's skeleton, revealing the hidden framework of fractures that accommodates tectonic motion. In volcanic regions, seismic tomography can image magma chambers and the conduits that connect them to the surface. These images show that volcanic systems are far more complex than simple reservoirs of molten rock, instead consisting of networks of interconnected chambers, dikes, and sills that extend deep into the crust. Earthquakes within these systems track the movement of magma, providing insights into the processes that lead to volcanic eruptions. The earthquakes associated with volcanic activity follow different patterns from those on tectonic faults, reflecting the unique physics of magma movement through solid rock. Volcanic earthquakes tend to be smaller and more frequent, creating continuous swarms of activity that can persist for months as magma slowly migrates through crustal rock. The signals they generate often have different characteristics from tectonic earthquakes, with longer periods and more complex waveforms that reflect the fluid nature of their source. These volcanic earthquake swarms can be remarkably beautiful when viewed as time-lapse animations, showing clouds of seismic activity that migrate through the crust like slow-motion fireworks. The patterns they create illuminate pathways of magma transport that connect deep magma sources to surface volcanic vents, revealing the plumbing systems that feed eruptions. Even in non-volcanic regions, earthquake patterns reveal the hidden flow of fluids through crustal rock. Groundwater movement, oil migration, and the injection of fluids for industrial purposes all generate characteristic earthquake signatures that can be distinguished from purely tectonic activity. These fluid-induced earthquakes typically occur at shallower depths and show temporal patterns that correlate with fluid pressure changes rather than tectonic loading cycles. The study of induced earthquakes has become increasingly important as human activities that involve large-scale fluid injection have expanded. Hydraulic fracturing, geothermal energy development, and wastewater disposal can all trigger earthquake activity by changing fluid pressures in fault systems that were previously stable. Understanding these processes requires combining knowledge of rock mechanics, fluid dynamics, and tectonic stress fields. Remarkably, even these human-induced earthquakes follow the same statistical relationships that govern natural seismic activity. The frequency-magnitude distribution remains consistent whether earthquakes result from tectonic loading or fluid injection, suggesting that the fundamental physics of rock failure operates the same way regardless of the triggering mechanism. This universality points to deep principles that govern how brittle materials fail under stress. The mathematical elegance of these relationships extends beyond earthquake statistics to encompass the mechanics of fault rupture itself. The way cracks propagate through rock follows equations derived from fracture mechanics, describing how stress concentrations at crack tips drive the expansion of fault surfaces during earthquakes. These equations predict rupture velocities, stress drops, and radiated seismic energy with remarkable accuracy. Laboratory experiments on rock samples confirm these theoretical predictions, showing how materials fail under controlled conditions that simulate earthquake processes. High-speed cameras capture crack propagation at velocities approaching the speed of sound in rock, revealing the detailed mechanics of rupture that occur too quickly to observe during actual earthquakes. These laboratory studies bridge the gap between theoretical understanding and field observations, validating the physical models used to interpret seismic data. The integration of laboratory, theoretical, and observational approaches has created a comprehensive understanding of earthquake physics that spans scales from microscopic crack growth to continental plate motions. This multi-scale perspective reveals earthquakes as manifestations of universal physical principles, governed by the same laws that describe fracture in materials ranging from glass to galaxy-spanning structures. At the largest scales, earthquake systems participate in the grand cycles of planetary evolution, contributing to the long-term recycling of crustal material and the gradual cooling of the Earth's interior. Each earthquake represents a tiny step in processes that operate over billions of years, slowly reshaping the planet's surface while maintaining the dynamic balance between heat generation and heat loss that keeps the Earth geologically active. This cosmic perspective transforms our understanding of seismic hazards from isolated threats to expressions of the planetary processes that make Earth a living world. the same forces that occasionally shake the ground are continuously working to maintain the conditions necessary for life, regulating climate through the carbon cycle, refreshing the atmosphere through volcanic outgassing, and generating the magnetic field that protects us from harmful solar radiation. In this broader context, earthquakes become not disruptions of natural order but essential components of the Earth system. They represent the planet's way of maintaining dynamic equilibrium, releasing accumulated stress through controlled failure rather than catastrophic collapse. Like the controlled burns that prevent forest fires from becoming unmanageable, earthquakes serve as pressure release valves that maintain stability within the larger tectonic system. The recognition of this stabilizing role has led some scientists to view earthquake prediction not as a goal to be achieved, but as a misconception based on incomplete understanding of complex systems. Rather than trying to predict individual earthquakes, the focus has shifted toward understanding the statistical properties of earthquake systems and their long-term evolution. This probabilistic approach acknowledges the inherent unpredictability of individual events while extracting useful information about overall system behavior. Modern seismic hazard assessment combines this statistical understanding with detailed knowledge of local fault systems to estimate the likelihood of strong ground shaking over specified time periods. These assessments don't predict when earthquakes will occur, but they provide quantitative estimates of seismic risk that inform building codes, insurance rates, and emergency preparedness planning. The approach recognizes uncertainty as an inherent feature of earthquake systems rather than a temporary limitation to be overcome. This acceptance of uncertainty paradoxically provides a more solid foundation for earthquake science than previous attempts at deterministic prediction. By acknowledging the limits of predictability, scientists can focus on understanding the aspects of earthquake behavior that are genuinely knowable while developing robust strategies for living with the aspects that remain uncertain. The result is a more mature and realistic approach to earthquake hazards that emphasizes preparedness over prediction. The engineering applications of this understanding have produced remarkable advances in earthquake-resistant construction. Modern buildings in seismically active regions are designed not to prevent earthquake damage entirely, but to fail gracefully, protecting human life, while accepting that some structural damage may occur during rare, very large earthquakes. This performance-based approach recognizes that perfect earthquake resistance is neither achievable nor necessary. Base isolation systems allow buildings to move independently of ground motion, dramatically reducing the forces transmitted to the structure during earthquakes. These systems work by inserting layers of flexible materials or mechanical devices between the building foundation and the ground, essentially decoupling the structure from seismic shaking. The result is buildings that remain nearly motionless even while the ground beneath them moves violently. Energy dissipation systems provide another approach to earthquake resistance, incorporating devices that absorb seismic energy before it can damage structural elements. These systems work like shock absorbers in automobiles, converting the kinetic energy of earthquake motion into heat through controlled deformation of specialized materials. Buildings equipped with these systems can withstand much stronger shaking than conventional structures while suffering minimal damage. The combination of these technologies with advanced structural analysis methods has made it possible to design buildings that can survive earthquake shaking that would have destroyed earlier structures. Computer simulations can now predict building response to earthquake motion with remarkable accuracy, allowing engineers to optimize designs for specific seismic environments. These advances represent a triumph of applied earthquake science, translating theoretical understanding into practical solutions that protect human life and property. The same computational tools used for structural analysis also enable detailed modeling of earthquake processes themselves. High-resolution simulations can reproduce the complete rupture process of major earthquakes, tracking how cracks propagate along fault surfaces and how seismic waves radiate outward through complex geological structures. These models provide insights into earthquake mechanics that would be impossible to obtain through direct observation. Large-scale earthquake simulations require some of the world's most powerful computers, solving equations that describe rock deformation across spatial scales, ranging from meters to hundreds of kilometers. The computational demands are enormous, but the results provide unprecedented views of earthquake processes that help scientists understand how fault systems behave and how seismic hazards vary across different regions. These simulations can also explore scenarios that haven't occurred historically, testing how fault systems might respond to different patterns of stress loading, or how earthquake sequences might unfold in ways that differ from past experience. Such scenario modeling provides valuable information for hazard assessment, particularly for regions where historical earthquake records are limited, or where fault systems may be capable of larger earthquakes than have been observed. The integration of computational modeling with observational data has created a new paradigm for earthquake science, where theoretical understanding, field observations, and numerical simulations work together to provide comprehensive insights into seismic processes. This multidisciplinary approach has accelerated progress in understanding earthquake systems while opening new avenues for practical applications. As monitoring networks become more sensitive and computational capabilities continue to expand, the resolution and scope of earthquake studies will continue to improve. Real-time earthquake monitoring already provides immediate information about earthquake location, magnitude, and shaking intensity, enabling rapid response systems that can automatically shut down critical infrastructure or alert emergency responders within seconds of large earthquakes. Future developments may extend this real-time capability to include detailed characterization of fault rupture processes, providing immediate insights into earthquake mechanics that currently require days or weeks of analysis. Such advances would further integrate earthquake science with engineering applications, creating closed-loop systems where observations immediately inform hazard assessment and risk mitigation strategies. The global nature of modern earthquake monitoring also enables studies of how earthquake systems interact across vast distances, revealing connections between seismic activity in different regions that operate on timescales ranging from minutes to millennia. These long-range interactions demonstrate that earthquake hazard assessment must consider not only local fault systems, but also their connections to regional and global patterns of seismic activity. Understanding these connections requires viewing earthquake systems as components of larger Earth systems that include not only solid rock, but also the atmosphere, oceans, and climate system. Earthquakes influence these other systems through processes like landslide generation, groundwater disruption, and volcanic triggering, while these systems in turn influence earthquake processes through loading effects, erosion patterns, and temperature changes that affect rock strength. This systems perspective reveals earthquakes as integral parts of Earth's complex adaptive behavior, participating in feedback loops that maintain planetary stability across geological time. Rather than random disruptions of an otherwise stable system, earthquakes emerge as necessary components of the dynamic equilibrium that characterizes our living planet. The study of earthquakes thus becomes a window into understanding how complex systems maintain stability through controlled instability, achieving long-term persistence through short-term variability. This insight has applications far beyond seismology, informing our understanding of everything from ecosystem dynamics to financial markets to climate system behavior. In this broader context, the gentle rhythms of earthquake cycles join the other great cycles that characterize Earth systems, from the daily rotation that brings sunrise and sunset to the orbital cycles that drive ice ages, to the tectonic cycles that build and destroy mountain ranges over hundreds of millions of years. Each operates on its own timescale, yet all interact to create the complex, ever-changing, yet fundamentally stable world we inhabit. As you rest tonight, these vast cycles continue their patient work around you. Tectonic plates drift with imperceptible motion. Stress accumulates grain by grain in fault zones. Seismic waves from distant earthquakes pass unnoticed through the bedrock beneath your home. The Earth's deep machinery operates in profound silence, following patterns established over billions of years of planetary evolution. This hidden activity connects your quiet moment of rest to processes operating across every scale of space and time, from the vibration of individual atoms in stressed crystal lattices to the grand circulation patterns that stir the planet's interior. You are part of this vast system, resting on a world that never rests, supported by forces that operate with patience beyond human comprehension. The earthquakes that occasionally remind us of these hidden processes are not interruptions of natural order, but expressions of it. Moments when the Earth's patient work becomes briefly visible in the language of motion and sound. They speak of balance maintained through change, of strength that comes from flexibility, of systems that persist by allowing parts of themselves to break and heal. In their mathematical precision, their statistical regularity, their connection to global processes, earthquakes, reveal a planet that operates according to principles of elegant complexity. They show us a world where apparent chaos emerges from deep order, where unpredictability at small scales gives rise to reliable patterns at larger scales, where destruction and creation work hand in hand to maintain the dynamic stability that makes life possible. This understanding transforms how we might think about the tremors that occasionally shake our world. Each earthquake becomes a note in a symphony that has been playing for billions of years, a composition written in the language of stone and time. The movements are sometimes barely perceptible, sometimes dramatic, but always part of a larger musical structure that extends far beyond any single performance. The instruments that record this planetary music have become extraordinarily sensitive, capable of detecting vibrations so subtle they make the precision of a Swiss watch seem crude by comparison. Modern seismometers can sense the Earth swaying gently in response to the gravitational pull of the Moon, measuring deflections smaller than the diameter of a hydrogen atom. These instruments reveal that our planet is never truly still, always humming with activity at frequencies too low for human ears to perceive. This constant background vibration creates what seismologists call the Earth's ambient noise field, a continuous chorus of tiny signals generated by ocean waves, wind patterns, and even the subtle expansion and contraction of rock as temperatures change throughout the day. Like a massive musical instrument being played by natural forces, the Earth generates harmonics and overtones that create complex interference patterns detectable by sensitive equipment around the world. The beauty of these measurements lies not just in their precision, but in what they reveal about the interconnected nature of Earth systems. A storm in the North Pacific generates microseisms that travel through solid rock to seismometers in Europe. Seasonal changes in snow load on mountain ranges create subtle flexing patterns that propagate across entire continents. The Earth responds as a unified whole to influences both large and small, demonstrating a sensitivity that extends across every scale of observation. This global sensitivity helps explain why some earthquake-triggering mechanisms operate across such vast distances. When a truly massive earthquake occurs, it sends waves racing around the planet that can arrive at the opposite side of the globe while still carrying enough energy to nudge already stressed fault systems into activity. The 2004 Sumatra earthquake was so powerful that it caused measurable changes in the Earth's rotation and triggered small earthquakes in regions as distant as Alaska and the western United States. These remote triggering effects operate through mechanisms that are still being studied, but they appear to involve the subtle changes in stress that occur as seismic waves pass through rock. Even though these stress changes are tiny compared to the forces normally required to cause earthquakes, they can provide just enough additional push to cause failure in fault systems that were already close to their breaking point. It's like the final straw that breaks the camel's back, except the straw might be delivered from halfway around the world. The mathematical models that describe these triggering processes reveal elegant relationships between wave amplitude, frequency, and the probability of inducing seismic activity in distant regions. These models show that the Earth's crust exists in a delicate state of balance, with many fault systems poised near their failure threshold, ready to respond to even subtle changes in their stress environment. This near-critical state is maintained by the constant loading of tectonic forces, which gradually increase stress on fault systems at rates that remain remarkably steady over human lifespans. The consistency of these loading rates reflects the deep stability of the mantle convection patterns that drive plate tectonics. Processes that operate with such regularity that they can maintain constant strain rates for millions of years. The precision of this geological clockwork becomes apparent when examining fault systems that have been monitored for decades using high-precision GPS measurements. These observations show that points on opposite sides of major fault zones move past each other at rates that can be measured to within fractions of a millimeter per year, revealing motion so steady it resembles the operation of mechanical devices rather than geological processes. This mechanical precision extends to the earthquake cycles themselves, with some fault systems producing ruptures at intervals so regular they approach the predictability of tidal cycles. The regularity emerges from the interplay between constant tectonic loading and the physical properties of fault zones, creating systems that store and release energy in highly organized patterns. The organization of these patterns becomes even more remarkable when viewed across networks of interconnected faults. Rather than operating independently, fault systems coordinate their behavior through stress transfer mechanisms that create coherent patterns of seismic activity across entire regions. When one fault ruptures, it changes the stress conditions on nearby faults in ways that can either hasten or delay their next earthquakes, creating complex cascades of seismic activity that unfold over decades or centuries. These stress transfer effects have been mapped in exquisite detail for well-studied fault systems like the San Andreas network in California, where decades of monitoring have revealed how earthquakes on different fault segments influence each other through the surrounding stress field. The resulting maps look like neural networks, showing pathways of mechanical communication that connect fault systems across hundreds of kilometers. The same stress transfer mechanisms that operate between faults also connect earthquake systems to other geological processes. Volcanic activity can load nearby fault systems with additional stress, while large earthquakes can trigger volcanic eruptions by changing pressure conditions in magma chambers. Landslides and glacial loading create their own stress patterns that influence seismic activity, while erosion and sedimentation gradually modify the long-term stress field that drives tectonic processes. These connections reveal earthquakes as components of integrated Earth systems rather than isolated geological phenomena. Understanding earthquake hazards requires considering not just fault mechanics, but also the broader environmental context in which fault systems operate. Climate change, for example, may influence earthquake patterns through its effects on glacial loading, sea level, and groundwater pressure, though these influences operate over timescales much longer than typical planning horizons. The long timescales involved in these interactions highlight one of the most remarkable aspects of earthquake systems: their ability to maintain coherent behavior across geological time. Fault systems that are active today show evidence of similar activity patterns extending back millions of years, suggesting that the fundamental organizing principles of seismic activity have remained stable across vast periods of planetary evolution. This stability reflects the deep connections between earthquake systems and the fundamental physics of planetary heat transport. The same convection patterns that drive plate tectonics also maintain the Earth's magnetic field, regulate surface temperature through volcanic outgassing, and control the long-term cycling of materials between the surface and interior. Earthquake systems are integral components of this planetary machinery, helping to maintain the dynamic equilibrium that has kept Earth habitable for billions of years. The magnetic field generated by this deep circulation creates an invisible shield that extends far into space, deflecting charged particles from the solar wind that would otherwise strip away our atmosphere. Without the continuous motion of electrically conducting fluid in the Earth's outer core, this protective field would decay within thousands of years, leaving the planet vulnerable to atmospheric erosion like that which occurred on Mars. The connection between earthquakes and magnetic field generation operates through the same convection processes that drive plate tectonics. Heat transport from the core to the surface powers both the fluid motions that generate magnetism and the solid-state convection that moves tectonic plates. Seismic waves provide one of the few direct ways to study these deep circulation patterns, carrying information about temperature and composition from regions that will never be accessible to direct sampling. Advanced seismic imaging techniques can now map convection patterns in the Earth's mantle, with resolution approaching that of weather maps, revealing plumes of hot material rising from the core mantle boundary and sheets of cold material sinking from subduction zones. These images show that mantle convection operates as a global circulation system, with upwelling and downwelling currents that connect surface tectonics to core processes through continuous loops of material transport. The timescales of this deep circulation are vast, with individual parcels of mantle rock taking tens of millions of years to complete journeys from surface to core and back again. Yet this slow stirring maintains temperature gradients that have remained stable for billions of years, providing the steady energy source that powers all surface geological activity. The stability of these deep processes helps explain why earthquake patterns, while unpredictable in detail, show statistical properties that remain constant across centuries of observation. The driving forces that load fault systems operate according to planetary scale processes that change slowly compared to human lifespans, creating the consistent boundary conditions necessary for statistical regularity in seismic activity. This regularity has enabled the development of probabilistic earthquake forecasting methods that can estimate the likelihood of future seismic activity without attempting to predict specific events. These methods recognize that individual earthquakes are inherently unpredictable while extracting useful information about the statistical properties of earthquake systems that can inform long-term planning and risk assessment. The mathematics underlying these forecasting methods draws from the same statistical physics that describes other complex systems exhibiting self-organized behavior. Earthquake systems show characteristics of critical phenomena existing near phase transitions where small changes can have large effects, yet maintaining overall statistical stability through feedback mechanisms that prevent complete system breakdown. This critical state behavior helps explain both the unpredictability of individual earthquakes and the remarkable consistency of earthquake statistics across different regions and time periods. Systems operating near critical points exhibit scale invariant behavior where patterns remain similar across different scales of observation, creating the power law relationships that characterize earthquake frequency distributions. The universality of these statistical relationships suggests that earthquake systems represent a fundamental type of complex behavior that emerges naturally in systems with many interacting components operating under steady driving forces. Similar patterns appear in phenomena ranging from forest fires to stock market fluctuations, indicating that earthquake statistics reflect general principles of complex system behavior rather than unique properties of geological processes. This broader perspective on earthquake systems has influenced approaches to seismic hazard assessment, shifting emphasis from attempts at deterministic prediction toward understanding the systematic properties that govern earthquake occurrence over long time periods. Modern hazard maps combine statistical analysis of historical seismicity with detailed geological studies of fault systems and physics-based models of earthquake processes. The resulting hazard assessments provide quantitative estimates of the probability of experiencing different levels of ground shaking over specified time periods, information that can be translated into building code requirements, insurance rates, and emergency planning scenarios. While these assessments cannot predict when specific earthquakes will occur, they provide essential guidance for making rational decisions about earthquake preparedness in seismically active regions. The development of these probabilistic approaches has coincided with remarkable advances in earthquake monitoring technology that provide unprecedented views of seismic processes in real time. Modern monitoring networks can detect and locate earthquakes within minutes of their occurrence, measure ground motion with precision that approaches theoretical limits, and transmit this information instantaneously to users around the world. Real-time earthquake monitoring enables rapid response systems that can provide immediate warnings of strong shaking to areas not yet reached by seismic waves. These earthquake early warning systems work because seismic waves travel at finite speeds through the Earth's crust, creating time windows of seconds to minutes between earthquake detection and the arrival of damaging waves at distant locations. While these warning times are brief, they can be sufficient for automated systems to halt elevators, shut down gas lines, stop trains, and alert people to take protective actions. The effectiveness of such systems depends on the speed of earthquake detection and the efficiency of communication networks, both of which have improved dramatically with advances in digital technology and high-speed data transmission. The same technological advances that enable real-time monitoring also support detailed studies of earthquake source processes that were impossible just decades ago. High-rate GPS receivers can track ground motion during earthquakes with millimeter precision, revealing how fault surfaces slip and how ruptures propagate in real time. Strong motion accelerometers record the complete history of ground acceleration during earthquakes, providing data essential for understanding how seismic waves interact with surface geology and engineered structures. These observational capabilities have revolutionized understanding of earthquake rupture processes, revealing that fault slip during earthquakes is far more complex and variable than early models suggested. Rather than simple, uniform rupture of planar fault surfaces, earthquakes involve intricate patterns of slip that vary dramatically in both space and time, creating complex radiation patterns that depend sensitively on the detailed geometry and mechanical properties of fault systems. The complexity of these rupture processes helps explain why earthquake ground motion prediction remains challenging, despite advances in understanding earthquake physics. Small variations in fault geometry, stress conditions, or rupture initiation can lead to large differences in radiated seismic energy, creating irreducible uncertainties in ground motion prediction that must be addressed through probabilistic methods. These uncertainties are not limitations to be overcome, but fundamental characteristics of earthquake systems that reflect the complex, nonlinear nature of rupture processes. Accepting these uncertainties as inherent features rather than temporary obstacles has led to more robust approaches to earthquake hazard assessment that explicitly account for the range of possible outcomes rather than seeking single-valued predictions. This probabilistic framework extends beyond ground motion prediction to encompass all aspects of earthquake risk assessment, from the likelihood of fault rupture to the performance of engineered systems during earthquakes. Modern earthquake engineering recognizes that perfect seismic resistance is neither achievable nor necessary, instead focusing on performance-based design approaches that allow controlled damage while protecting These life approaches have led to remarkable innovations in earthquake-resistant construction, including base isolation systems that decouple buildings from ground motion, energy dissipation devices that absorb seismic energy before it can damage structural elements, and smart materials that can adapt their properties in response to earthquake shaking. The integration of advanced material science with earthquake engineering has produced structures that can survive ground motion levels that would have destroyed earlier buildings, while suffering minimal damage themselves. Modern seismic design approaches recognize earthquakes not as external threats to be resisted, but as natural phenomena to be accommodated through intelligent engineering that works with seismic forces rather than against them. This philosophy of accommodation rather than resistance reflects a broader shift in how earthquake hazards are conceptualized. from unpredictable disasters to manageable risks that can be addressed through appropriate planning, design, and preparedness measures. This shift has been enabled by the scientific understanding that reveals earthquakes as expressions of orderly natural processes rather than random catastrophes. The patterns that govern earthquake occurrence operate across every scale of space and time, from the microscopic processes that control rock failure to the global circulation patterns that drive plate tectonics. Understanding these patterns provides a foundation for rational approaches to earthquake risk that neither ignore seismic hazards nor treat them as incomprehensible threats beyond human understanding. The mathematical relationships that describe earthquake statistics reveal a world where apparent randomness emerges from underlying order, where complex behavior arises from simple rules, and where unpredictability at small scales gives rise to reliable patterns at larger scales. These insights transform earthquakes from arbitrary disasters into expressions of natural law, governed by the same physical principles that describe all phenomena in the natural world. As you settle deeper into rest, these mathematical harmonies continue their patient work around you. Stress accumulates in fault zones according to equations that describe elastic deformation. Energy dissipates through rock networks following pathways determined by fracture mechanics. Seismic waves propagate through the Earth's interior according to wave equations that govern all forms of mechanical vibration. The precision of these physical laws extends from the smallest scales, where individual atoms respond to stress according to quantum mechanical principles, to the largest scales, where entire continents drift according to the laws of fluid dynamics applied to solid rock. At every level, the same fundamental physics governs behavior, creating nested hierarchies of pattern and process that connect earthquake occurrence to the deepest principles of natural science. This scientific understanding reveals earthquakes as part of the grand tapestry of natural phenomena that includes everything from the formation of crystals to the evolution of galaxies. Like these other natural processes, earthquakes follow mathematical laws that create beauty through complexity, generating patterns that are both surprising and inevitable, chaotic and ordered, destructive and creative. The study of these patterns has become one of the great intellectual adventures of modern science, connecting fields as diverse as materials science, fluid dynamics, statistical physics, and planetary science in efforts to understand how complex systems maintain stability through controlled instability. Each earthquake becomes a natural experiment that tests our understanding of these fundamental processes. The insights gained from earthquake studies have applications far beyond seismology, informing our understanding of how complex networks maintain resilience, how critical systems manage risk, and how emergent properties arise from the interactions of many simple components. These lessons apply to everything from ecosystem management to financial system stability to the design of robust technological networks. In this broader context, earthquakes become teachers as well as phenomena to be studied, revealing principles of system behavior that can guide human efforts to build resilient societies in an inherently uncertain world. The same adaptive strategies that allow fault systems to maintain long-term stability while accommodating constant stress can inform approaches to managing other types of systematic risk. The patience required to study earthquake systems also provides lessons in how to approach complex problems that unfold over timescales much longer than human attention spans. Understanding earthquake processes requires thinking in geological time, where significant changes occur over centuries or millennia rather than seasons or years. This perspective can help develop more sustainable approaches to other long-term challenges facing human societies. The collaborative nature of modern earthquake science also demonstrates how complex problems can be addressed through coordinated efforts that span disciplines, institutions, and national boundaries. Global earthquake monitoring networks require international cooperation to maintain, while understanding earthquake processes draws on expertise from fields ranging from physics to computer science to social science. These collaborative efforts have created a scientific community that shares data, methods, and insights across traditional boundaries, working together to build understanding that no single group could achieve alone. The resulting knowledge belongs to all humanity, providing foundation for informed decisions about earthquake risk, regardless of political or economic circumstances. The instruments that make this global collaboration possible operate continuously, quietly recording the Earth's seismic activity and transmitting their observations to data centers where they become part of the growing archive of earthquake information. This archive now contains records spanning more than a century of systematic observation, creating an unprecedented database for studying long-term patterns in seismic activity. The analysis of these historical records reveals that earthquake systems exhibit both stability and change over time, maintaining their fundamental statistical properties while showing subtle variations that reflect changing stress conditions and evolving fault system properties. Understanding these variations requires statistical methods that can separate genuine trends from random fluctuations in datasets that span decades or centuries. These statistical challenges are similar to those faced in climate science, where long-term trends must be distinguished from natural variability in systems that exhibit complex, multi-scale behavior. The methods developed for earthquake analysis have contributed to broader advances in time series analysis and statistical modeling that have applications throughout the earth sciences. The computational requirements for analyzing these large data sets have driven advances in high-performance computing and data management that benefit many fields of scientific research. Modern earthquake catalogs contain millions of events with associated measurements of location, magnitude, and source characteristics, creating databases that require sophisticated algorithms for efficient storage, retrieval, and analysis. Machine learning techniques have become increasingly important for extracting patterns from these vast data collections, identifying subtle signals that would be impossible to detect through traditional analysis methods. Neural networks can recognize characteristic patterns in seismic waveforms that indicate specific types of earthquake sources, while clustering algorithms can identify previously unknown relationships between different types of seismic activity. These automated analysis methods are particularly valuable for processing the continuous streams of data generated by modern monitoring networks, where human analysts could never examine every signal manually. Computer algorithms can scan thousands of seismic recordings per day, identifying events of interest and characterizing their properties with precision that rivals or exceeds human capabilities. The automation of routine data processing has freed earthquake scientists to focus on interpreting results rather than generating them, leading to more rapid advances in understanding earthquake processes. Real-time analysis systems can now provide immediate characterization of earthquake source properties, enabling rapid assessment of earthquake impacts and more timely warnings of potential hazards. These technological advances continue to accelerate, with new generations of instruments providing ever greater sensitivity and new analysis methods, extracting ever more information from the resulting data. The future promises even more detailed views of earthquake processes, with monitoring networks that can track fault system behavior in real time and predictive models that can assess changing earthquake probabilities as stress conditions evolve. Yet even as our technical capabilities expand, the fundamental insights about earthquake systems that emerge from current research emphasize continuity rather than revolution. The mathematical relationships that govern earthquake occurrence appear to be universal and stable, reflecting deep physical principles rather than temporary artifacts of limited observation. This stability provides confidence that current understanding captures essential truths about earthquake systems that will remain valid as knowledge continues to expand. These enduring truths include the recognition that earthquakes are expressions of planetary-scale processes rather than isolated geological events, that they follow statistical laws that create order within apparent chaos, and that they serve essential functions in maintaining the dynamic equilibrium that characterizes Earth systems. Understanding earthquakes requires appreciating them as components of integrated natural systems rather than external threats to human activities. This systems perspective transforms earthquake hazard from an external risk to be defended against into an environmental condition to be accommodated through appropriate adaptation strategies. Like other environmental factors such as weather, earthquakes become part of the natural context within which human societies must function, requiring thoughtful planning and design but not fundamentally threatening the possibility of safe and prosperous communities. The engineering solutions that enable safe construction in earthquake-prone regions demonstrate that human ingenuity can successfully adapt to seismic hazards when guided by sound scientific understanding. Modern earthquake-resistant buildings represent triumphs of applied science, translating theoretical knowledge about ground motion and structural dynamics into practical technologies that protect human life and property. These technological solutions continue to evolve as understanding of earthquake processes improves and new materials and construction methods become available. Smart structures that can adapt their response to earthquake motion in real time, advanced materials that become stronger under stress, and predictive systems that can anticipate structural performance during earthquakes all represent frontiers of earthquake engineering research. The same innovative approaches that have revolutionized earthquake-resistant construction are being applied to broader questions of societal resilience, including how communities can maintain essential functions during and after major earthquakes. These efforts recognize that earthquake impacts extend far beyond structural damage to include disruptions of economic activity, social networks, and psychological well-being that can persist long after physical damage is repaired. Building truly resilient communities requires understanding not only the physical aspects of earthquake hazards, but also the social, economic, and psychological factors that determine how communities respond to and recover from seismic events. This multidisciplinary approach to earthquake risk combines insights from engineering, social science, economics, and public health to develop comprehensive strategies for earthquake preparedness. The resulting understanding reveals that earthquake resilience is not simply a matter of building stronger structures, but of creating adaptive communities that can maintain their essential functions even when confronting unexpected challenges. This broader view of resilience has applications beyond earthquake hazards, informing approaches to managing other types of systematic risks that threaten community stability. The lessons learned from studying earthquake impacts and recovery processes contribute to a growing body of knowledge about how complex social systems respond to disruption. These insights help explain why some communities recover quickly from disasters while others struggle for years, and they provide guidance for policies and practices that can enhance community resilience across a range of potential hazards. This research has revealed that the most resilient communities are those with strong social networks, diverse economic bases, effective governance systems, and cultures that emphasize adaptation rather than rigid adherence to fixed plans. These characteristics enable communities to respond creatively to unexpected challenges and to learn from experience in ways that increase their capacity to handle future disruptions. The parallels between community resilience and the adaptive behavior of natural systems like fault networks suggest that similar principles may govern the stability of complex systems across many different domains. Understanding these universal principles could provide insights into how to design more robust institutions, economies, and technologies that can maintain their essential functions even when confronting significant disruptions. As you rest in the quiet of this moment, these insights into resilience and adaptation continue to unfold around you through countless natural and human systems. The fault networks beneath your feet maintain their stability through millions of years of gradual adjustment to changing stress conditions. The communities you're part of adapt continuously to evolving challenges through the collective intelligence of their members. Both natural and human systems demonstrate that true stability comes not from rigidity, but from flexibility. Not from avoiding change, but from managing it skillfully. The earthquakes that occasionally remind us of these hidden processes are expressions of this deeper wisdom, showing us how powerful forces can be accommodated through patient adaptation rather than futile resistance. In their mathematical precision, their connection to global processes, and their role in maintaining planetary habitability, earthquakes reveal a world where apparent chaos serves essential functions, where destruction and creation work together to maintain dynamic balance, and where understanding replaces fear when we learn to see the deeper patterns that govern natural processes. The gentle rhythms of these vast systems continue their patient work as you settle into sleep, following patterns established over billions of years of planetary evolution, maintaining the conditions that make this quiet moment of rest possible. In the grand symphony of Earth systems, even your peaceful breathing becomes part of the harmony connected to every other process through the web of relationships that bind all phenomena together in one magnificent, ever-changing, ever-stable whole. The mathematics that describe earthquake triggering reveal patterns so elegant they resemble musical compositions written in stone. When seismic waves from distant earthquakes travel through the Earth's crust, they create stress changes that follow predictable wave equations, rising and falling in amplitude, according to principles that govern all forms of mechanical vibration. These passing waves can nudge fault systems that are already close to failure, providing just enough additional stress to trigger ruptures that might otherwise wait years or decades to occur. The beauty of this process lies in its sensitivity. Stress changes smaller than those caused by atmospheric pressure variations can sometimes trigger earthquakes in regions thousands of kilometers from their source. It's as if the Earth's crust exists in such a delicate state of balance that even the gentlest touch can cause dramatic responses, like a perfectly balanced scale where a feather's weight determines which way it tips. This exquisite sensitivity extends to other subtle influences on earthquake timing. The gravitational pull of the moon and sun creates tiny periodic stresses in solid rock, similar to ocean tides but measured in centimeters rather than meters. These earth tides follow the same mathematical relationships that govern ocean tides, creating predictable patterns of stress that cycle through peaks and valleys twice each day. While these tidal stresses are minuscule compared to the forces that drive most earthquakes, statistical studies have found weak correlations between tidal cycles and earthquake occurrence in some regions. The effect is subtle, detectable only through careful analysis of thousands of earthquakes, but it demonstrates once again how interconnected Earth systems are, with influences from space reaching deep into solid rock to affect the timing of geological processes. The same gravitational forces that create Earth tides also influence the planet's rotation, causing tiny variations in the length of each day that can be measured with atomic precision. These rotational changes redistribute stress within the Earth, creating another pathway through which astronomical cycles might influence seismic activity. The connections operate across vast scales of space and time, linking earthquake occurrence to the orbital mechanics of the solar system. Even seasonal changes in atmospheric pressure and groundwater levels create measurable effects on earthquake rates in some regions. As winter storms increase atmospheric pressure or spring snowmelt raises groundwater tables, the additional weight pressing down on the Earth's surface can slightly modify stress conditions on nearby fault systems. These seasonal influences are typically small, but they add another layer to the complex web of factors that determine when and where earthquakes occur. The study of these subtle triggering mechanisms has revealed that earthquake systems exist perpetually near critical thresholds, poised to respond to influences so gentle they would be imperceptible in most other contexts. This near-critical state is maintained by the constant background loading of tectonic forces, which gradually increases stress on fault systems, while various smaller influences provide the final triggers that determine precise timing. Understanding these triggering relationships has practical implications for earthquake hazard assessment, particularly in regions where large earthquakes might trigger cascades of smaller events on nearby fault systems. The stress changes caused by major earthquakes can persist for years or decades, gradually dissipating as the surrounding rock adjusts to new configurations. During this adjustment period, aftershock sequences follow mathematical decay laws that describe how the rate of smaller earthquakes decreases over time. The most famous of these relationships is Omori's law, discovered in the 1890s, which describes how aftershock rates decrease inversely with time after main earthquakes. This mathematical relationship holds remarkably well across different regions and earthquake sizes, suggesting that it reflects fundamental aspects of how rocks respond to sudden stress changes. The universality of Omori's law provides another example of the deep mathematical order that underlies apparently chaotic earthquake processes. Modern variations of Omori's law include additional parameters that account for the specific characteristics of different earthquake sequences, but the basic inverse relationship between aftershock rate and elapsed time remains one of the most robust statistical relationships in seismology. This predictability allows scientists to forecast the general evolution of aftershock sequences, even though individual aftershocks remain unpredictable. The spatial patterns of aftershocks also follow statistical laws that illuminate the three-dimensional structure of fault systems. Aftershocks cluster near the original rupture zone in patterns that reveal how stress changes propagate through networks of interconnected fractures. These patterns typically show exponential decay with distance from the main shock, creating halos of seismic activity that gradually fade as distance increases. Combining the temporal and spatial patterns of aftershock sequences creates four-dimensional pictures of how fault systems adjust to major stress changes. These pictures show clouds of seismic activity that migrate through the Earth's crust over time, following pathways determined by the geometry of fracture networks and the direction of stress changes caused by the original earthquake. The beauty of these migrating aftershock patterns becomes apparent when viewed as time-lapse animations, where months or years of seismic activity compress into minutes of viewing time. The resulting displays look like slow-motion fireworks exploding underground, with clusters of activity blooming and fading according to mathematical rules that govern stress diffusion through fractured rock. These same principles that describe aftershock sequences also apply to earthquake swarms, clusters of seismic activity that occur without a single dominant main shock. Swarm activity often indicates fluid movement through fracture networks, with earthquake patterns tracing the pathways along which water, magma, or other fluids migrate through the Earth's crust. The mathematical relationships that describe these patterns are similar to those governing aftershocks, but with modifications that reflect the different physical processes involved. Volcanic earthquake swarms provide particularly clear examples of how fluid movement creates characteristic seismic signatures. As magma moves through networks of fractures beneath volcanoes, it generates continuous sequences of small earthquakes that track the migration pathways in real time. These earthquakes typically have different spectral characteristics from tectonic events, with longer periods and more complex waveforms that reflect the fluid nature of their source. The patterns created by volcanic earthquake swarms can be remarkably organized, showing systematic migration from deep magma sources toward the surface along pathways that illuminate the internal plumbing systems of volcanic edifices. Time-lapse visualizations of these swarms reveal branching networks of seismic activity that resemble root systems or river deltas, following paths of least resistance through the complex three-dimensional structure of volcanic systems. Even in non-volcanic regions, earthquake swarms can reveal hidden aspects of crustal structure and fluid flow. Geothermal areas often experience swarm activity as heated groundwater moves through fracture networks, while regions of active faulting may show swarms associated with slow slip events that release tectonic stress gradually rather than in single large ruptures. These slow slip events represent another fascinating aspect of fault system behavior, showing that not all tectonic motion occurs through sudden earthquake ruptures. Some fault zones accommodate plate motion through gradual sliding that can last for weeks or months, releasing as much energy as major earthquakes, but so slowly that the motion produces only tiny seismic signals detectable by the most sensitive instruments. The discovery of slow slip events has revolutionized understanding of fault system behavior, revealing that the boundary between earthquake rupture and steady sliding is not as sharp as previously thought. Instead, fault systems show a continuous spectrum of slip behaviors, from instantaneous rupture to steady creep, with slow slip events occupying intermediate positions in this spectrum. The mathematical models that describe these different slip behaviors are based on the same friction laws that govern everyday phenomena, like the sliding of objects across surfaces, but applied to fault surfaces under enormous pressures and temperatures. These models show that small changes in fault zone properties can lead to dramatically different behaviors, explaining why some faults produce large earthquakes, while others slip steadily without generating significant seismic activity. Laboratory experiments on rock samples confirm these theoretical predictions, showing how materials transition between different failure modes as conditions change. High-pressure, high-temperature experiments can simulate the conditions that exist on fault surfaces deep in the Earth's crust, revealing how rock friction varies with sliding velocity, normal stress, and temperature in ways that determine whether faults slip steadily or rupture suddenly. These laboratory studies bridge the gap between theoretical understanding and field observations, providing controlled environments where individual variables can be isolated and studied systematically. The results help calibrate the mathematical models used to simulate earthquake processes and predict how fault systems might respond to changing stress conditions. The integration of laboratory experiments, theoretical modeling, and field observations has created a comprehensive framework for understanding earthquake physics that spans scales from microscopic grain boundaries to continental plate motions. This multi-scale approach reveals that the same physical principles operate at every level, creating nested hierarchies of behavior that connect atomic-scale processes to planetary-scale phenomena. At the smallest scales, earthquake nucleation begins with the breaking of chemical bonds between mineral grains, processes governed by quantum mechanics and statistical thermodynamics. These microscopic failures cascade upward through larger and larger scales, eventually producing macroscopic fault ruptures that can extend for hundreds of kilometers and release energy equivalent to thousands of nuclear weapons. The mathematical description of this cascade process draws from theories developed to understand phase transitions in material science, where small changes in local conditions can trigger system-wide changes in material properties. Earthquake nucleation resembles these phase transitions, with critical phenomena occurring when stress conditions reach thresholds where stable sliding becomes unstable rupture. The critical nature of earthquake nucleation helps explain both the unpredictability of individual events and the statistical regularity of earthquake occurrence over longer time periods. Systems operating near critical points exhibit extreme sensitivity to small perturbations while maintaining overall statistical stability, creating the paradoxical combination of chaos and order that characterizes earthquake systems. This critical behavior extends beyond earthquake nucleation to encompass the entire rupture process. Once fault rupture begins, its propagation follows dynamics similar to crack growth in other materials, with rupture velocity determined by the balance between driving stress and fracture resistance. These dynamics create complex rupture patterns that vary dramatically from earthquake to earthquake, even on the same fault system. High-resolution studies of earthquake rupture processes reveal intricate patterns of slip that vary both spatially and temporally during individual events. Rather than simple, uniform sliding along planar fault surfaces, earthquakes involve complex distributions of slip that create irregular patterns of stress release and seismic wave radiation. These patterns help explain why earthquake ground motion prediction remains challenging, despite advances in understanding basic earthquake physics. The complexity of earthquake rupture processes reflects the heterogeneous nature of fault zone properties, which vary continuously along fault surfaces due to differences in rock type, stress history, and chemical alteration. These variations create a landscape of stronger and weaker patches that control how ruptures propagate and where they stop, adding another layer of complexity to earthquake behavior. Computer simulations of earthquake rupture can now reproduce many observed features of real earthquakes, including complex slip distributions, variable rupture velocities, and realistic seismic wave radiation patterns. These simulations require enormous computational resources, solving millions of equations simultaneously to track how stress and motion evolve throughout three-dimensional fault systems during rupture processes that last only seconds or minutes. The computational demands of these simulations have driven advances in high-performance computing that benefit many fields of scientific research. Earthquake simulations routinely use some of the world's most powerful supercomputers, pushing the boundaries of what's possible in terms of spatial resolution, temporal accuracy, and physical realism. Despite their complexity, these numerical simulations reveal underlying patterns in earthquake behavior that reflect the operation of relatively simple physical laws. The same principles that govern crack propagation in laboratory specimens also control fault rupture in the Earth's crust, scaled up by factors of millions in size and time, but following identical mathematical relationships. This universality of physical laws across different scales provides confidence that laboratory studies and computer simulations can provide genuine insights into earthquake processes that occur under conditions impossible to study directly. The mathematical relationships discovered in controlled laboratory experiments apply equally well to fault ruptures that extend for hundreds of kilometers through the Earth's crust. The validation of these theoretical frameworks through comparison with field observations has created a mature science of earthquake physics that can explain most observed features of seismic activity. While individual earthquakes remain unpredictable, the statistical properties of earthquake systems and the physical processes that control rupture dynamics are now well understood. This understanding provides the foundation for probabilistic approaches to earthquake hazard assessment that can estimate the likelihood of different levels of ground shaking over specified time periods. These assessments combine statistical analysis of historical seismicity with physics-based models of earthquake processes and detailed knowledge of local geological conditions to produce quantitative estimates of seismic risk. Modern seismic hazard maps represent the culmination of decades of research in earthquake science, translating theoretical understanding into practical information that can guide building codes, insurance rates, and emergency planning decisions. These maps show the probability of experiencing different levels of ground shaking, typically expressed as the chance of exceeding specific acceleration values during 50-year periods. The mathematical methods used to create these hazard maps draw from probability theory, statistics, and decision analysis to combine multiple sources of uncertainty in coherent frameworks that can handle the inherent unpredictability of earthquake systems. The resulting assessments acknowledge uncertainty as a fundamental characteristic rather than a temporary limitation to be overcome. This probabilistic approach to earthquake hazards has transformed how seismic risk is conceptualized and managed, shifting focus from attempting to predict specific events toward understanding the statistical properties of earthquake systems that remain stable over long time periods. The approach recognizes that perfect prediction is neither achievable nor necessary for effective risk management. The same statistical methods used for seismic hazard assessment also apply to other types of systematic risks that exhibit similar characteristics of unpredictability combined with statistical regularity. Financial markets, ecological systems, and technological networks all show power law distributions and critical phenomena similar to those observed in earthquake systems. These parallels suggest that earthquake science has contributed to broader understanding of how complex systems behave, providing insights that extend far beyond seismology to inform approaches to managing systemic risks across many domains. The mathematical tools developed for earthquake analysis have found applications in fields ranging from economics to epidemiology to climate science. The interdisciplinary nature of modern earthquake science reflects the recognition that understanding complex systems requires integrating knowledge from many different fields. Earthquake studies now routinely combine expertise from physics, geology, engineering, computer science, mathematics, and social science to address questions that no single discipline could answer alone. This collaborative approach has accelerated progress in understanding earthquake systems while creating new opportunities for cross-fertilization between different fields of research. Methods developed for earthquake analysis have contributed to advances in material science, while techniques from other fields have enhanced earthquake research capabilities. The global nature of earthquake hazards has also fostered international cooperation in earthquake science, with researchers from many countries working together to share data, develop common analysis methods, and build theoretical frameworks that apply worldwide. This cooperation has created a truly international scientific community dedicated to understanding earthquake processes and reducing seismic risk. The data sharing that enables this international cooperation operates through networks of seismic monitoring stations that provide real-time information about earthquake activity around the world. These networks represent one of the most successful examples of international scientific collaboration, maintaining consistent data standards and open access policies that benefit researchers everywhere. The continuous operation of global seismic monitoring networks generates enormous volumes of data that document earthquake activity with unprecedented completeness and precision. This growing archive of seismic observations provides an invaluable resource for studying long-term patterns in earthquake occurrence and testing theoretical models against real-world data. Analysis of these historical records has revealed subtle but systematic changes in earthquake patterns that occur over timescales of decades or centuries, reflecting the gradual evolution of stress conditions within fault systems. Understanding these long-term variations requires statistical methods that can distinguish genuine trends from random fluctuations in data sets that span many decades. The temporal patterns discovered in long earthquake records show that seismic activity clusters in time as well as space, with periods of increased activity alternating with quieter intervals in cycles that can persist for centuries or millennia. These temporal clusters reflect the complex interactions between different fault systems and the gradual redistribution of stress that follows major earthquakes. Spatial clustering of earthquake activity creates patterns that illuminate the hierarchical structure of fault networks, showing how smaller faults connect to form larger systems that accommodate regional tectonic motion. These hierarchical patterns follow scaling relationships similar to those observed in river networks, demonstrating another example of how similar mathematical principles govern diverse natural phenomena. The fractal geometry of fault networks creates patterns that look similar at different scales of observation, from microscopic fractures in rock samples to continental-scale fault systems that bound tectonic plates. This scale invariance suggests that the same physical processes control fracture formation across the entire range of scales relevant to earthquake occurrence. Understanding these scaling relationships has practical implications for earthquake hazard assessment, as they provide ways to extrapolate from well-studied regions to areas where earthquake data are limited. The universal nature of these scaling laws allows researchers to make reasonable estimates of earthquake potential in regions where direct observations are sparse. The mathematical beauty of these scaling relationships extends beyond their practical utility to provide deep insights into the fundamental processes that shape the Earth's crust. The power laws that describe fault network geometry and earthquake statistics reveal underlying principles of organization that emerge from the interaction of simple physical rules operating across vast ranges of space and time. These emergent patterns represent one of the most profound aspects of earthquake science, showing how complex, organized behavior can arise from relatively simple underlying processes. The same principles that govern individual crack growth also determine the statistical properties of earthquake systems that encompass entire continents. This emergence of order from apparent chaos reflects the deep mathematical structure that underlies all natural phenomena, connecting earthquake science to broader questions about how complexity arises in physical systems. The patterns discovered in earthquake research contribute to understanding complexity as a general feature of natural systems rather than a unique property of geological processes. As you continue to rest, these patterns of emergence and organization continue their quiet work throughout the Earth's crust. Stress accumulates gradually along fault surfaces according to the patient rhythms of tectonic loading. Fracture networks evolve slowly toward configurations that optimize stress distribution. Earthquake cycles progress through their mathematical sequences with the reliability of celestial mechanics. The precision of these natural processes operates at scales both vast and intimate, from the planetary circulation patterns that drive plate tectonics to the molecular scale processes that determine rock strength. Every level of organization follows mathematical laws that create harmony between apparent randomness and deep order, between unpredictability and statistical regularity. In the gentle mathematics of these geological rhythms, there's something profoundly soothing about recognizing that even the Earth's most dramatic processes follow patterns of elegant simplicity. The same equations that describe the vibration of a guitar string also govern the propagation of seismic waves through continents. The same principles that explain how crystals grow also determine how fault networks develop their fractal geometry. This mathematical unity reveals a world where everything connects to everything else through relationships of profound beauty and surprising simplicity. In earthquake science, as in all natural philosophy, the deepest truths are often the most elegant, expressing complex phenomena through relationships so fundamental they approach the status of universal laws. The continuing discovery of these relationships transforms our understanding of earthquakes from chaotic disruptions to expressions of natural harmony, from unpredictable disasters to manifestations of planetary processes that have maintained Earth's habitability for billions of years. In this perspective, even the ground's occasional trembling becomes part of a vast symphony of geological processes that creates the stable foundation upon which all life depends. As these thoughts settle gently around you like layers of sediment accumulating on an ocean floor, the Earth's patient processes continue their eternal work. Tectonic plates drift with imperceptible motion. Stress builds grain by grain in fault zones. Seismic waves from distant earthquakes pass unnoticed through the bedrock beneath you. And in the mathematical precision of these vast cycles, there is peace. The instruments that record these planetary harmonics have reached such extraordinary sensitivity that they can detect the Earth's response to weather systems thousands of kilometers away. When massive storm fronts move across ocean basins, they create pressure waves that travel through the solid Earth faster than the storms themselves, arriving as gentle whispers in seismograph records before meteorologists even detect the atmospheric disturbances that cause them. These meteorological signals blend with the constant chorus of microseisms generated by ocean waves, creating a background symphony that plays continuously beneath our feet. The mathematics that describe this oceanic music follow the same wave equations that govern all forms of mechanical vibration, but scaled to planetary dimensions and played at frequencies so low they require sensitive instruments to detect. During winter months in the Northern Hemisphere, this seismic symphony grows louder as storm systems intensify, sending stronger signals through the Earth's crust. The seasonal variations in background noise follow patterns so regular that seismologists can predict them months in advance, creating another layer of mathematical order within the apparent chaos of global seismic activity. These predictable patterns extend to the solid Earth tides caused by lunar and solar gravity, which create rhythmic flexing of the entire planet with periods that match celestial mechanics. The ground beneath you rises and falls by several centimeters twice each day, following gravitational forces with such precision that atomic clocks can detect the resulting changes in gravitational acceleration. The mathematics of these tidal deformations involve the same gravitational field equations that describe planetary orbits, but applied to the elastic properties of solid rock rather than the motion of celestial bodies. The resulting calculations reveal how the Earth responds as a unified elastic body, deforming smoothly in response to external forces while maintaining its overall structural integrity. Tonight, we've journeyed through the hidden mathematics of our restless planet, discovering that even the Earth's most dramatic moments follow patterns of profound gentleness. From the patient drift of continents to the elegant equations that describe seismic waves, we've found that earthquakes are not chaotic disruptions, but expressions of a deeper harmony that has been playing for billions of years. As you drift towards sleep, let these geological rhythms carry you into dreams, knowing that the very ground beneath you participates in cycles of such patient beauty that they transform our understanding of what it means to rest on a living world.